The papers we will discuss today are the European Roadmap towards Fusion Electricity, Chapter 4, Heat Exhaust Systems. In ITER, the steady-state heat loads on the target plants in the diverter will be in the order of 10 MW per meter square under detached plasma conditions transiently during edge-localized modes. The heat loads can reach levels of a few gigawatt per meter square during pulses of typically 0.5 to 1 milliseconds plasma phasing. Components need to withstand these heat loads for a sufficiently long time to avoid too frequent shutdowns to replace them. Demo will feature much longer pulses, while it has much thinner wall than ITER, which comes from the fact that the neutrons should not lose their energy in the wall, but in the breathing blanket behind it. And therefore, it is necessary to develop highly radiative plasmas for demo in which most of the outgoing energy is uniformly radiated from the plasma edge. Mission 2 of the European Roadmap is based on 3 pillars. 1. Develop routine and robust control systems for plasma detachment in a conventional diverter geometry. 2. Develop, improve, and test new diverter materials and plasma-facing components. 3. Test alternative magnetic geometries to spread the plasma heat load over a larger surface of the diverter jet and the 3 medium-size tokamaks ASDEX upgrade, TCV, and must upgrade are being used to test diverter detachment as well as alternative diverter geometries. The ultimate test of controlled diverter detachment with a conventional diverter will be in ITER during diverter detachment. The electron temperatures in front of the diverter are reduced to values below approximately 5 electron volt, such that recycled neutral particles from the target plates undergo a number of charge exchange collisions with plasma ions before they are ionized. As a result, the plasma flow to the target plates becomes more diffusive and is strongly reduced. The TCV tokamak exploits the snowflake diverter geometry, in which the heat load from the plasma is split over 4 instead of 2 footprints, thus lowering the maximum heat load on the diverter plates. To enhance its flexibility, the diverter of TCV is being equipped with 2 high-TC superconducting coils. In must upgrades, the Super X geometry will be tested. In this concept, the outer diverter plates are located at the largest plasma radius that is possible inside the toroidal field coils to increase the plasma wetted area. ASDEX upgrade, in its turn, will be equipped with upper diverter such that it can study plasma in the so-called double null configuration. All three devices have the possibility to study multiple geometries. Finding the optimum diverter geometries is one part of the challenge. The second part is to find diverter geometry that is demo compatible, as it makes so sense to use a diverter in demo that uses magnetic coils that are placed very close to the plasma and that are therefore very vulnerable to the neutron bombardment coming from the plasma. Liquid metal targets are among the new materials that are being investigated. They have the advantage that the diverter is in principle self-healing in case material is evaporated. Drawbacks are the possibility of droplets that may enter the plasma and the fact that the desired flow pattern might be affected by the magneto hydrodynamic forces in the tokamak. It will also be necessary to develop a scheme in which the loop of the liquid flow is closed so that the material cannot accumulate in the plasma or the vessel. Eurofusion is exploiting a range of devices to test plasma-facing components. These include the superconducting Magnum PSI liner plasma simulator, which can mimic heat loss exceeding 10 MW per meter square in steady-state conditions, as well as pulsed heat loss up to 1 GW per meter square to mimic edge localized modes. DUDITH can test materials with an intense electron beam, while the superconducting West tokamak will test an actively cooled diverter under similar power loads as in ITER. Thanks for listening to the end of today's show.